we're doing is we're estimating the slope of the line. So we've graphed this function y equals 3 to the x. We're looking for the tangent to the curve right at this point and just estimating the slope of this line is about 1.1. So my goal here is to get a base for my exponential function so that the slope of the tangent line to the exponential function at the point 0,1 will give me a slope of exactly 1. And that's how we define the number e. It's in between 2 and 3. So what is e? 2.718, etc., because it's irrational, infinitely expanding decimals. And if we use that for our base, then when we graph e to the x, we're going to get a tangent of exactly 1. So x is 0, y is 1. X is 1, y would be e. What's e? 2.718. I'm going to put it approximately there. Negative 1, you'd get about 1 over 2.718. So from here on, I'm going to have a slope of the tangent line to this curve will be exactly 1. So when I graph this, it's going to bounce off of my ruler right there. So the slope of the tangent line to this curve, that slope is exactly 1. So this is your function e to the x. We looked at it in Math 12 as the limit of that sequence. That is, we looked at e as the limit as k approaches infinity of 1 plus 1 over k to the power of k. That's what gave us the number e. And how do we get e to the x? It was the limit as k approaches infinity, 1 plus x over k to the power of k. That limit is e to the x. That's what we did in Math 12. In calculus, we're going to look at the number e as being the base of the exponential that will give you a slope of a tangent line of 1 at the point 0,1. Is going to come up frequently. You need to know all the details of it. So it's exponential growth because the base is e, a number bigger than 1. So exponential growth it has a domain of all reals. It's got a range y greater than 0. Of course, it's got a horizontal asymptote along the x-axis, aka y equals 0. We call that an increasing function. So we're going to take that and do some transformations on it. Ready? So we know what the base function e to the x looks like. What does 1/2 e to the minus x minus 1 look like? E to the x has a domain of all reals and a range of y strictly greater than 0. It has a horizontal asymptote along the x-axis, aka y equals 0. What kind of transformations do we have? So a vertical compression of 1/2. Then x goes to minus x will reflect it in the y-axis, as in flip it backwards, and the minus 1 will move it 1 down. Okay, so we know that our horizontal asymptote is flipping 1 down, is moving 1 down. So our horizontal asymptote is going to be here. This reflection in the y-axis is going to take this function, this exponential growth, and turn it into exponential decay. That's e to the minus x in red. It's going to flip the orientation of that graph. And the vertical compression is just going to make all of my y values half the size. Can you remember how to write a mapping for this kind of a transformation? Any point xy on the original graph mapped over to negative x because we reflect it across the y-axis. What happens to the y's? They're all 1/2 as big, and we move them 1 down. So we've got a key point on this graph right here. Put it through the mapping. What happened to the point x is 0, y is 1 under this kind of a transformation? Negative 0 is still 0. 1/2 of y, 1/2 of 1 is a half. Subtract 1, I've got negative a half. So x is 0, y is negative a half, and we're going to graph this. So it's going to look something like that. By the way, if I asked you to find the x-intercept, would you know how to do it? Do it then. Okay, you substituted 0 in for y, and now you want to isolate your exponential. So we're going to add 1 to both sides. Now what are we going to do? Are we? We're going to multiply both sides by 2. You were saying divide by 1/2, same as multiplying by 2. So I get 2 is equal to e to the minus x. In the next lesson we'll talk about this, but I'll just throw this in here quickly. You're trying to solve for a variable and an exponent. You all want to take the log of both sides, don't you? When the base is e, use ln, such as the ln of 2 is equal to the ln of e to the minus x, because the ln is just log to the base e, same number. Ln laws will work the same as exponent laws. We'll have ln 2 equals negative x times the ln of e. Why don't you grab your calculators and find out what the ln of e is? Somebody said it already. How do you know it's 1? Because the ln of e means log to the base e of e. How would you do it on here? Press your ln button and put e in there. What's the ln of e? It's 1. Right under log. Here's your log button, here's your ln button. How do you find e? Second divide. Okay, so ln 2 would give me negative x times 1. Ln of e is 1. Or negative ln 2 would give me x. Okay, what's the ln of 2? Ln 2. Negative 0.69. So check your graph. Is that about where we've got it? About there. So what's my x-intercept? About negative 0.69 when y is 0. Okay, for what values of x will e to the x be bigger than 1,000,000? As in, what power do I raise e to in order to get a number bigger than 1,000,000? How would I solve that? So e to the x bigger than 1,000,000. If that was 10 to the x, you'd know the answer to that, wouldn't you? What would it be? Yeah, 6. It'd have to be bigger than 6. What about if it's e to the x? How are you going to solve that? You're going to take the ln of both sides. Your power law brings that x down in front. What's the ln of e?
1.
1. I need x to be bigger than the ln of 1, 2, 3, 4, 5, 6, a million. I need x to be bigger than 13.8. So I guess 14 would be, e to the power of 14 would be bigger than a million. E to the power of 15, as long as my exponent is bigger than 14. You guys did homework this weekend that you're going to show me later when I come around. I would like you to now do the questions that you omitted. So take a couple minutes and look those over. Okay, so if our function is x cubed, our inverse function, exchange x and y, solve for y, our inverse function is cube root of x. Remember function composition. Tell me, what is f composed of f inverse x? Well, function composition is just substitution. We're going to have f acting on f inverse. Composition is substitution. What's f inverse? Cube root x. So f acts on the cube root of x. What does f do to its input? It cubes it. So this would be the input cubed. What am I putting in? The cube root of x. And if I cube the cube root of x, what do I get? X. Every time you compose a function with its inverse, you will get x. Every time you compose an inverse with a function, you will get x. If you don't, it's not the inverse. Okay, so it's a really important concept. A function composed of its inverse is x. How come? Well, because the inverse just undid whatever the function was doing. Okay, so if I was cubing it, and now I cube root it, well, I just get back to my input. Okay, so let's take that and look at some specific numerical examples. If the function at 1 is 5, and the function at 3 is 7, and the function at 8 is negative 10, what's the inverse at 7? Well, this particular function has this in its domain. Let me do a cloud diagram for you. It took 1 over 2, 5 in the range. It took 3 over 2, 7, and it took 8 over 2, negative 10. Okay, the function does that. What does the inverse do? Well, the inverse will undo what the function did. It takes 7 to 3. The inverse undoes what the function just did. That is, it's going to take 5 back to 1. What happens to negative 10? You get 8. So for the inverse, the domain becomes the old range. The range becomes the old domain. Okay, so when we say this, f inverse x equals y, it means the function at y equals x. If I take an inverse and compose the function, I get x. If I take function and compose it with inverse, I get x. If this doesn't happen, you don't have the inverse. How do we find an inverse of a function? I think in Math 12 we did the order a little bit differently. It doesn't really matter, but we write y equals f at x, and then we interchanged x and y and then solved for y. I think in your textbook they take y equals f at x and they solve it for y and then they exchange it. It doesn't matter which order you do that in. Let's do a little bit of practice. Can you find the inverse of this function? So we're going to start out writing y equals x cubed plus 2. If I'm finding the inverse, I exchange x and y. That is, x equals y cubed plus 2. And then I solve it for y. Subtract 2 from both sides. isolate the y by taking the cube root of both sides, and I get y equals the cube root of x minus 2. So what is the inverse function? F inverse x is equal to cube root x minus 2. Let's go back to the original function, this one right here. What's the domain for a cubic? And the range for a cubic? All reals. The inverse function, cube root, what's the domain? And the range? All reals. Right, you can take the cube root of a negative. Okay, graphically or visually, remember that when you're taking the inverse, you are reflecting it over the line y equals x. Let's graph this function and its inverse on the same grid. So before I start, I'm going to write this radical function in preferred format, factoring out that -1. Because I know what this function y equals root x looks like. It looks like this. Okay, from your catalog of basic functions in Math 12, there's root x. What kind of transformations do I have? Well, x goes to -x, meaning I've got a reflection in the y-axis, aka I'm flipping that backwards. And that +1, remember we had to factor out the leading coefficient, is saying that this moves 1 to the left. So I'm going to flip this backwards and move it 1 to the left. So instead of looking like this, it's going to look like that. And 1 to the left, it starts here. And then this one would go over here. And then this one would be -1, 2, 3, 4, and 1 to the left. So this function would look like this. Okay, so here is f at x. What does the inverse look like? So I'm not asking you to find the inverse, I'm just asking you to graph the inverse. When you graph the inverse, you exchange x and y. So this point, -1, 0, becomes the point 0, -1. This point, -2, 1, becomes the point 1, -2. This point, 1, 2, 3, 4, 5, -5, 2 becomes the point 2, -1, 2, 3, 4, 5. So it's going to look like that. Remember we took this and we reflected that green function across the line y equals x.